Hi everyone, this video will walk you through lesson 11.8, which will teach you about geometric probability. In this particular section, you're going to learn that we can use the concepts of probability using basic geometric principles that you've learned throughout this unit specifically in regards to area and length. So you can solve these probability problems in this section using one of the two following principles as listed at the top here. So if we look at the first principle here, suppose a point P of the segment AB is picked at random. One of the first things that will be helpful in these problems, more often than not, is to make a sketch. So you can see here, I'm going to sketch segment AB, and I'm going to go ahead and put another point on the segment, because again, we can do that with any segment, and just call it point C. It doesn't really matter where. To find the probability that point P is picked at random, we need to figure out the probability that point P would be on the smaller of the segments. So I'm going to find the probability, which is that capital P out in the front, and in parentheses, just to shorthand that point P is on segment AC. The way that I would be able to find that is to find the length of AC and compare that to the overall length of the segment AB. So ultimately, I'm trying to find wherever P would be randomly placed. What I can then use that for is to ultimately figure out how the lengths kind of compare to one another and the probability of selecting it and placing it in the spot that I'm trying to do so. Now, I can also apply this concept to area. So in number 2 here, it says, suppose a point P of region S is picked at random. So I'm drawing any region. You can see the squiggles there. So I have this big region S, and I assume wherever I pick point P from would be from this smaller subregion within S, and I'm just going to call that R, just for the sake of using the alphabet here. What that would allow me to do is to find the probability of point P within that smaller region, and ultimately, I can compare the areas to one another. So I can find the probability that that point lands in a certain spot within the overall region by finding the area of the smaller region, R, and comparing it to the area of the larger region, S. Now, with all of these here, again, you'll be able to do some of your basic probability math where you'll be able to reduce your fractions and turn things into percentages. We'll see that in a couple spots. But ultimately, with these problems here, some of you are going to be able to solve them without having to do much in the way of sketching. For all of these, I'm going to show you a way that you can sketch them out for those of you that learn a little bit better visually. So there's 3 problems we're going to walk through here. Let's talk about the first one. So we're going to go ahead and use some geometric probability in number 1. Every 10 minutes, a shuttle pulls up to a hotel and waits for 2 minutes while passengers get on and off. Then the shuttle leaves. If a person walks out of the hotel at a random time, what is the probability that a shuttle is there? Now, I think out of the problems I'm going to show you here today, this is probably the one where you may not need a picture for it, but I can show you via number line using length how we can figure that out. So the rotations of this shuttle, they come every 10 minutes, so I could draw a number line from 0 to 10. And you can see my wonderfully accurate drawing of a shuttle bus that doesn't look like a very large shoe at all. It's going to be there for 2 minutes, let some people off, let some people on, and then it's going to drive away. For the remaining 8 minutes, there's no shuttle in front of the hotel. So if the question is here, what's the probability that the shuttle is there? All I'm going to do is compare, well, how long is the shuttle there versus the total amount of time the shuttle is driving around back and forth before making stops at the hotel. So it'd be 2 minutes out of 10. This would reduce to 1 out of 5, which you could also convert to a percentage. You can convert that to 20%. And some of these, converting into a percentage is how you may see it represented as well. The second one, you do have to use some more geometric properties here, if you will, and ultimately you have yourselves what looks to be a archery board of some sort here. So a person who's just beginning archery lessons misses the target frequently, but when the beginner hits the target, each spot is likely to be hit as another. So if the beginner shoots an arrow and it hits somewhere, anywhere on the target, what is the probability, that the arrow hits the bullseye? So if we look at our generic target here, our bullseye is the centermost circle, and that would be the circle with a radius of 1. So what I would want to do in this case is to compare the area of the bullseye to the area of the entire circle. So the area of my smallest circle, the bullseye, would be equivalent to pi times 1 squared. The overall circle, the area of that would be pi times 3 squared, because 3 is the radius of the overall large circle. Of course, from here, we can reduce it to pi over 9 pi. Our pi's would cancel out, leaving us with a 1 out of 9 probability that will hit the bullseye as long as we hit the target. Convert that to a percentage, it'd be 11.1 repeating percent. So again, instance there where more you do have to use a little bit of geometry, and certainly the diagram will help you figure out how ultimately you can solve it with the correct measurements that are there. This last one here, we are going to make a sketch for sure because we are dealing with some measurements and it'll be easier to kind of see where everything fits if we sketch this out. So carnival game, you toss a coin on a large table that has been divided into squares 30 millimeters on the side. So I'm going to go ahead, I'm going to draw a square, and we're going to go ahead and put in our different measurements. I'm going to back up here a step before we get to that point. So 30 millimeters square. The coin has to come to a rest without touching any line of this square. So it's a carnival game. You're trying to fit it totally within the square, not hitting any of the borders of it. Otherwise, you lose your coin, you lose your game. What are the chances of winning on one toss of a dime? Now, a fact that you need to know in order to solve this, a dime has a radius of 9 millimeters. So that's going to be important because halfway across that dime is 9 millimeters. We got to keep the size of it in mind to figure out how much space you actually have in order to ultimately fit it within the square itself. So there's probably a couple ways you can figure this out, but from a visual perspective, if my radius is 9, that means the center of my dime has to be at least 9 millimeters away from all of my sides. So what I'm going to do here is I'm going to create a grid, and I'm basically mapping out on the left, the right, and the vertical up and down. I want to make sure I am 9 millimeters away from each of my 4 sides. So you can see a bunch of 9s kind of labeled out here to try to avoid hitting the side of that square. What that means is the center of my dime needs to be in the center of this entire square. So this shaded region that I'm coloring in, that's where the center of my dime needs to be. Because if my center is within the shaded region, that means I'm at least 9 millimeters away from each of my sides, no matter where it lands in that shaded region. So because I'm 30 millimeters the whole way across or vertically, that means that square in the middle, each side of it is 12 millimeters, because 9 plus 9 would be 18, subtracted away. So I have a 12 by 12 square in the middle. In order to find that probability, we are going to go ahead and ultimately compare the area of the shaded square to the overall square itself. So basically, I'm going to write in a little note here that verbalizes what I just said here a minute ago. Might be worth jotting down to figure out why in the world we set this up the way that we did. And now we can get to the point of going ahead and computing what would be the chance of getting that dime to land in a place where we would win this game. So again, we are comparing the shaded area, so this 12 by 12 square, compared to the overall square, which would be 30 by 30. So 12 squared over 30 squared. So if you evaluate that out, it's 144 over 900, which is a very reducible fraction to 4 out of 25. This one I'll also convert to a percent, so again, you can see that it is a lot of times used as a percentage, and you might see that as you come across the problems here in the homework, 4 out of 25 being the same thing as 16%. So that's what geometric probability is. It's the same probability you essentially know. It's the chance of something you want to have happen versus all the possible outcomes that can occur. Just with this, it's more using what you know about the structure of some geometric figures, using some length, using some area to ultimately make a visual representation to find the probability of what you want to have happen. So, with that being said, that's your lesson on geometric probability. Make sure to complete the homework for 11.8, and again, the answer key there is posted, so feel free to consult that, work with each other, figure out what you're doing with that. If you finish that up, please keep in mind that you do have a test coming up on Tuesday the 29th. So over the weekend, if you need something to do, you can certainly work on some of the chapter review, chapter tests, self-test stuff in the book. Otherwise, thanks for taking the time to watch this. Have a great rest of your day. Enjoy your weekend.